In this video, we're looking at questions number 16 through 22 from your final exam review. All of these questions have something to do with transformations of parent functions. In this first question, we've got a graph with a dotted line that represents the parent function and a solid line which represents a transformation of that parent function, and we're asked to write the equation of the transformed graph. So first of all, looking at my parent graph, I notice that the function here is y equals absolute value of x. And to this parent function, we've made two transformations. First of all, the parent function has been reflected over the x-axis. And when we reflect a function over the x-axis, that transformation looks like y equals negative f of x. We're going to take whatever our function is and put a negative in front of it to cause that vertical reflection. The other transformation is that the graph has been translated to the right 3 units. And since this is a horizontal transformation, we're going to change something with the x part of our function. And in this case, we've moved to the right 3 units, and so it's going to be x minus 3. And so if we put those two transformations together with our parent function equation, the equation of this graph is going to be y equals negative absolute value of x minus 3. Let's look at question number 17. In this graph, it looks like our parent function graph here is y equals the square root of x. And again, we've got two transformations that have occurred. First of all, we're reflecting our parent function over the y-axis. So this time it's a horizontal reflection, and that means that I need to be making some kind of change to the x. We're going to do that, represent that transformation by making the x negative. That's what gives us that horizontal reflection. Our parent graph has also been translated up 2 units, and so that transformation, y is equal to f of x plus 2. We're going to add a 2 to our parent function. So if we group both of those transformations together with our parent function, y equals the square root of negative x plus 2, outside of the square root sign because we're adding 2 to the whole function. All right, let's look at question number 18. In this graph, our parent function is y equals x squared. And again, I think we've got two transformations here. First of all, the graph has been reflected over the x-axis, and so we remember that transformation, y equals negative f of x. But we've also had a narrowing of the graph. Notice that the transformed graph is more narrow than the parent function. It's been vertically stretched, and so we're going to represent that transformation. We're going to multiply by 2, and that's going to vertically stretch our graph. So if we put those two together, y is equal to negative 2x squared. And finally, number 19. In this graph, our parent graph here is y equals natural log of x. And again, we've done two transformations. Notice that, first of all, notice that my x-intercept for my parent graph is here at 1, and that's being shifted over here to 2. It's been shifted right 1 unit, and so we already know what that transformation looks like. It's going to be x minus 1. We're shifting to the right 1 unit, so x minus 1. But notice that in my transformed graph, everything is positive. This piece down here, which was negative, has been flipped upward. The negative part has become positive. And the way that we achieve that with a graph is to use the absolute value as a transformation. When I add absolute value to another function, it works like a transformation, and it takes everything that's negative and flips it up and makes it positive. So we're going to put those two things together to write the equation of this graph. Y is equal to the absolute value of the natural log of x minus 1. All right, let's move on to number 20. Here we've got a graph of a piecewise function, and in number 20 we're asked to write the equation for the piecewise function. Now if I look at the graph of this function, I can see that we've got three pieces. There's a parabola piece over here on the left, and then I've got a linear piece here, and then another linear piece here. And so we need to write the equations for all three of those pieces. Let's start with the parabola. So our function here, f of x, is equal to, remember with a piecewise function, we use the bars like this. And on the parabola, I notice that my vertex is here. It has the coordinates -3, 2. And what that means is that my vertex, which started at 0, 0, my parent function vertex is at 0, 0, we've shifted it left 3 units and up 2 units. And so I have those two transformations going on. I also notice that my graph has been reflected over the x-axis. It's now opening down instead of up like the parent function. And so that means that my whole function is going to be negative. Additionally, I notice that there's a stretch. The parent function graph of x squared starts from the vertex, and the next point would be over 1 and up 1, or in this case over 1 and down 1 since we flipped the graph over. But if I go over 1 and down 1, let me fix this. If I go over 1 and down 1, I'm not on the graph. The next point on my graph is actually over 1 and down 2. And that means that I've had a vertical stretch of 2. So let's put all of these transformations together. First of all, the graph has been reflected over the x-axis, so that means it's going to be negative. We've had a vertical stretch of 2, so we're going to multiply times 2. We've had a horizontal translation of -3. We've gone to the left 3 units, so that's going to be represented as x plus 3. And then our vertex has also been translated up 2 units plus 2. And I forgot, this is a quadratic. I need to square that x plus 3. So that would be the equation of this graph. Now since this is a piecewise graph, we're limiting the domain for each of the pieces, and so I need to include that in the equation of my function. And so I noticed that for this piece we're starting here at 1, 2, 3, -4 and going through -2. So -4 less than or equal to x less than or equal to -2. And you know, we really can't tell if at -2 the point is included on the parabola or the line. I'm just going to include it here and not on the line. All right, let's move on to the next piece. This piece of the graph, we just have a linear equation, and since we can easily see the y-intercept, it's convenient to use y equals mx plus b form to write this equation. The slope of this line is up 1 over 2. So slope is 1/2. The y-intercept is 3. And so we can write that equation as 1/2 x plus 3. And the domain for that piece, it's starting at -2. And it's continuing all the way to +2. So my line, the pink line here, is going from -2 to +2. So -2 less than x. I'm not going to say less than or equal to, because if I did that, this would no longer be a function. We would have two different y values at -2. -2 less than x, less than or equal to +2. And now we're on the last piece. Now again, my last piece here, it is a linear equation, but what's a little more challenging about this one is that we can't easily tell what the y-intercept is. In this case, it's going to be a lot easier for us to use point-slope form. And so I'm going to remind us about point-slope form up here. That equation is y minus y1 is equal to m times x minus x1. And in order to use this equation, I need to know the slope. And so I'm looking at my line here. My slope is down 2 and over 1, so it looks like my slope is negative 2. And then I also need some point that's on the line. I'm going to choose this point down here just for convenience. It has the coordinates 4, 0. And so that's going to be my x1, y1. So I end up with y minus 0 is equal to negative 2 times x minus 4. And so that equation, since it's y minus 0, that's just y equals, see if I can squeeze it in here, y equals negative 2x plus 8. So negative 2x plus 8. And that piece of our graph, it starts at negative 2, I'm sorry, not at negative 2, at positive 2, and continues to 4. Positive 2 less than x less than or equal to 4. Now for this particular graph, since these two pieces, the two lines, since they connect at this point here at 2, 4, we could actually put less than or equal to on both pieces because we're not defining two separate points for x equal to 2. There's the same point, and so it would still be a function. All right, let's move on to question number 21. In 21, we're asked to describe the domain and the range of this piecewise function as it's shown here. So my domain, I'm starting, the domain, remember, is your x coordinates that are included in the function. We're starting over here to the left. The furthest point is over here at negative 4. And it continues all the way to positive 4. And it looks like every point in between, every x value in between is defined on the function. And so that domain would be negative 4 less than or equal to x less than or equal to 4. Or you could write that as negative 4 to 4 using interval notation. For the range should include all the y values that are included in the function. And you know what, let's do a different color for range. For the range, my lowest points are actually all three of these points. They all have a y value of 0. That's my lowest value. The highest value, the maximum, is up here at this point, which would be at y equals 4. And every point in between 0 and 4, they're all defined on the graph somewhere. And so the range here is 0 less than or equal to y less than or equal to 4. Or if you prefer interval notation, 0 to 4. All right, I believe we've got one more question here. Question number 22. In this question, it says the function shown above, or on my slide here, the function shown to the left, is discontinuous at negative 2. So that's pointing out right here, there's a break between those two graphs. It's discontinuous. And it says describe a transformation that would make the graph of the function continuous. So we want to do something to one of the pieces of this graph so that the whole graph is continuous. And I have two choices. I could take this linear piece and move it down to connect with the parabola down here. Problem if I do that is then I'm causing discontinuity over here because I'm separating it from the other line. So a better choice for us would be to take the parabola piece and move it up until it connects right here. So that means that I need to move this up 2 units. So let's see, it said describe the transformation. So translate the parabola up 2 units.